Good morning everyone! We want to present you our project which is maze solving by memristive network. Initially, what is a maze? The maze is a complex branching passage where there is one enter and where the solver must find the correct path in order to exit from it. We propose a network consisting of memristors and switch in order to solve maze problems. Here the switch represents the walls of the maze, while the memristors represent the roots by themselves. The reason why memristors are used is that memristance is a charge-dependent variable. There are two kinds of maze problems which could be solved with our memristive network. The first is one-path problem. Here you can see the maze with only one correct exit path. By opening and closing the switch, we built the same maze using memristive network. And by simulation, we found that there is some current through particular memristors while there is no for others. We found that the sequence of memristors through which the current flows represents the correct exit path from the maze. Now let's move to the second kind of maze problems, which are more complicated. They are problems with several exit paths, and now my partner will talk about it.
Maze solving with several exit paths. Here we have the random maze. In order to exit the maze we have three passes, and it's obviously seen that the path 1 is the shortest one and path 3 is the longest one. Now we have constructed the same maze by using the memristors, whereas the interest of the maze is the voltage source and the exit is the ground. That's how the circuit will look like on LT-SPICE, and the simulation gives these results. It is clearly seen that the voltage drop across the first branch is much higher than the second one and the third one, and the same behavior for the currents. Memristor change its value within the time, and memristor change can be calculated by using this formula, where the voltage drop is divided by the current through this memristor minus 4 times R initial. Observing the plot that we have obtained from the LT-SPICE software, we can calculate the memristor change with respect to time for these three branches. By using the data from the previous table, we have constructed the visual representation of the memristor change over the time. It's clearly seen that the first branch exhibits greater memristor change in comparing with other two branches. Now we visually represent how we're gonna use the memristor change values in order to solve maze problem. As we know, the first branch is the shortest one, and the third branch is the longest one. Therefore, the higher value of memristor change represents the shortest path. However, within the time, the memristor change will show higher values in every three branches. Let's apply all this stuff in order to solve this random maze. Here is the result. The shortest path is colored close to red one. To conclude, we have observed the memristor that can help to solve maze in massively parallel way. This was experimentally proved by using system of memristors, resistors, and LT-SPICE software. Furthermore, implementation of the maze solving logical algorithm with memristive networks will find huge usage in different areas, such as subway road mapping.